In this video, we will talk about a test that is used to detect general functional form misspecification. And this is called a Ramsey's reset, or in other words, the Ramsey's regression specification error test. Now, let's consider an original model that's written out in this form. Okay, this is pretty standard. You know, this is a multiple linear regression model, right? It has multiple explanatory variables. And so here, we want to think a little bit about going back to our fourth assumption, which was of zero and conditional mean. If that condition is satisfied, then we would not expect any nonlinear functions of our x's or of our independent variables to be significant if we added those to our regression, right? So this is basically saying that if we regressed y on, let's say, beta 1 x1 plus beta 2 x2, and then we added, let's say, beta 3 x1 square plus beta 4 x2 square, and these are, you know, we are introducing nonlinearities here by introducing or incorporating nonlinear functions of the original explanatory variable. So if we introduce those, then we would expect that these estimates, right, when you estimate the model, these estimators would be insignificant if there were no nonlinearities in our model, okay? But we always want to check that, right? So that's the idea here, and that's why we want to always think about improving our model. So we always want to check if there is some relationship that we're missing between y and, let's say, the quadratic form or some other functional form of our explanatory variables. So the reset helps us do this. So the first thing you want to remember is when you're implementing reset, you need to decide how many functions of the fitted values to include in an expanded regression, which is to say that do you want to incorporate just quadratic terms, or do you want to also incorporate cubic or other higher order polynomials? Typically, quadratics are just sufficient, okay? But I'm going to show you an example where we're incorporating or testing for quadratic as well as cubic. The reason we use the fitted values from our original regression, so what we usually do is we basically just take this simple model where x1 and x2 are appearing in levels. We're not taking quadratics. We estimate this model and we get the fitted values, y hat, right? Once we get y hat, we would estimate a bigger regression in which you have everything is the same until this point, right? Until this point, everything is the same. You have all the x's appearing in level form, but then we incorporate the fitted values in quadratic form and in cubic form and whatever else you want to do. And then you're going to basically check what is the F statistic on those deltas that are appearing as coefficients on those fitted values, the quadratic and the cubic form of the fitted values. So we're basically testing for the F statistic here. And if you were just testing for, you know, just one of these, that would be a t-test. But a significant F statistic, right, or an F stat with a very low p-value, less than 5%, let's say, where the p is 0.05 or less, that is going to signal some form of functional form misspecification in your original regression. So that would basically signal to you that maybe you want to think about adding some explanatory variables in quadratic form or cubic form in this case, right? But obviously you don't have to do cubic, you can just stop at quadratic. And also, you know, because it's an F test, you can always make it robust to heteroscedasticity like we discussed in the previous chapter. So this is something to remember, and obviously here we know that this F statistic is going to follow, for this particular model, is going to follow this type of F distribution, because we have n minus k minus 3 degrees of freedom here. Okay, so we're estimating k coefficients, right, or parameters for the x's, and then we have one intercept and two coefficients to two of those deltas, so that makes it 3.